So far, we have learned a lot about the direct stiffness approach. The basic formulations have been well understood, and after that, we have also considered the case of applying temperature fluctuations and also the situation arising out of the hinges, both internal as well as external. Now we take one more step. So now we introduce the case that, let's say, the members are non-prismatic. So far we had made the assumption that we are dealing with prismatic members only. So all the relations including the member stiffness matrix, they were valid for prismatic members only. Now we remove this assumption and we consider general sections, that is, we have non-prismatic members. So let us first consider determinate structures and see how we deal with the approach while dealing with the determinate structures. So in determinate structures, if we encounter the application of loads and there is an elastic displacement, then the advantage of determinate structures is that both member end forces as well as the deflections, they can be directly obtained without bringing compatibility conditions. In general, for solving any analysis problem, we need to work out with equilibrium conditions along with the compatibility conditions so that we can get the force displacement relations. Now here, in the case of determinate structures, we can use any of the methods such as moment area method, conjugate beam method, or energy methods such as the principle of virtual work to obtain the displacements. Now when we talk of energy methods, we need to obtain the work done. So typically, if force P acts and under side P there is a displacement delta, assuming that both the force and the corresponding displacement, which are elastic, have increased gradually, in that particular case the work done by the force is half P delta. This is because it's basically the area under the P delta curve. Now when we talk of the virtual work, then our definition will be slightly different, as we'll see. Now if we want to use the principle of virtual work to solve this problem to find the deflection, all we have to do is that if bending mode is the predominant mode of deflection, we have to obtain the bending moment diagram. So once we have the bending moment diagram, then we apply at the point where we want displacement a virtual force of unit value. So virtual force is assumed to be a very infinitesimally small force as compared to the actual load, so that it does not bring about any changes in the system. So once we have the bending moment diagram for the actual load, we also obtain the bending moment diagram corresponding to the virtual force. Then what we do, we equate the external virtual work with the internal virtual work, and here the difference comes that when we talk of the virtual work, so we again calculate the area under the force displacement curve. So here we assume that the virtual force, it rides along the displacement caused by the real force, that is P. So as it rides along the displacement, then it carries out the virtual work, and this virtual work is not half V delta but it's equal to V delta, because the entire force V has been acting in full. So for this particular case, where we have now the bending moment diagrams of the two cases, the external virtual work is equated to the internal virtual work. The external virtual work is simply 1 into delta, because 1 is the value of the virtual force, and the internal virtual work is done by the integration consisting of the bending moment diagrams, the bending moment diagram for the real load uppercase m, and the bending moment diagram for the virtual load lowercase m. Their product divided by EI, and we do its integration along the entire length of the member. So this gives us the value of the delta. So point to be noted is that basically if the member is non-prismatic, then basically EI takes care of this fact. So here I is, for example, varying linearly for this particular member. So here it's a linear function in the denominator. So that's why when we solve the equation, we'll get something of log function sort. So here the conclusion that comes out is that for determinate structure, both the member end forces and the deflections, they can be easily computed by incorporating the variation of EI, and this is quite simple and straightforward. But now when we come to indeterminate structure, we encounter problems. If the structure we are dealing with, it has non-prismatic members. So the problem is that if the member is non-prismatic in nature, and let's say we want to derive the member stiffness matrix of the particular member in full, say 6 by 6, then we have to use the first principles, and the first principles, if we try to apply on a non-prismatic member, then we are stuck. So we are stuck here because now we don't have the standard force displacement relations. For example, here we have applied unit rotation, and we want to find out the relationship between the corresponding moment and this rotation. Now because the member is non-prismatic, we don't have any standard relation. Here if we want to use the classical force method, we can use it, but it will be highly tedious. So the basic slope deflection formulations which we have been using so far for deriving the members of the stiffness matrix of the member, they are no longer valid, and the use of the classical force method is very tedious. Again, if we want to use the principle of virtual work, we are stuck because now the structure is indeterminate. Being indeterminate, we do not know its bending moment diagram. So when we don't know the bending moment diagram, we cannot apply this to derive the displacement. So how do we solve? We'll use a different approach, but we have cleverly chosen the approach such that it helps us in easily achieving our purpose. And this is the flexibility method. There's a reason behind why we have chosen flexibility method. While we are doing right now the topic of the stiffness method, but we have inadvertently brought flexibility method so as to obtain some kind of help. Now, what is flexibility method and why do we use it? First of all, we must see the definition of the flexibility. Just like we have defined the stiffness coefficient Kij as the force required to bring about unit displacement along a particular degree of freedom. So that is the particular stiffness coefficient Kij. That is, we want to find out how much force is required along the degree of freedom I to induce unit displacement along the degree of freedom J. Now similarly, when we define a flexibility coefficient, we have to be cautious. So Fij, the flexibility coefficient, is basically the displacement along the line of action of the ith force when we apply unit force along the line of action of the jth force, such that. Now after this there is a rider, but before that we must define what is the line of action of force. In the force method, we don't talk about the degrees of freedom. Just like we talk about the degrees of freedom in the case of the stiffness approach, in force method we don't talk about the degrees of freedom. We have basically the forces as the main unknowns, and we talk about lines of action of the force. However, here we are using both the stiffness approach and the flexibility approach concurrently. So therefore, we will be using the terms like the degrees of freedom and lines of actions of forces concurrently or interchangeably. So basically here the rider is that when we are applying such force, then the condition is that there is no force acting along the lines of action of any other designated forces. So that means there is no other restraint. So what is the advantage? Because here there is no other restraint, so the member is basically a simple determinate structure, so it is easy to solve it, at least in a manner such that we can apply the principle of virtual work. So in the case of the stiffness approach, now which emphasizes that we have to lock all degrees of freedom except the one along which we are applying the particular displacement. Here the process is different. Here we have to create releases. Here we have to make sure that force is acting only along one particular line and there is no force acting along any other line. Again, we must emphasize that when we are talking about force, this includes both force as well as moment. Similarly, when we are talking about displacement, we are meaning both translations as well as rotations. So how it works and how we take advantage, we'll just see. So basically, let's say we have a non-prismatic member and here we are showing the degrees of freedom and these are also the lines of action of the forces. So to distinguish between the displacements and the forces, what we do is that we show the displacements by very thick lines or thick arrows or thick curves, and the forces we show by thin lines or single arrows. So here what we do, that to begin we apply a unit force along the degree of freedom 3, which is also the line of action of the force 3, and we do such that there is no force acting along any other degree of freedom or lines of action of the designated forces. How do we do this? We have to first create a basic structure which is stable. So that's why we first of all create here the minimum restraints. And now in this particular structure we apply our condition. So what we do, we apply a unit force. So we are showing here the forces by thin lines and thin curves, and all the displacements and the rotations, they are shown by these kind of thick lines or arrows. So we have applied here a unit moment. So by definition, this particular rotation, this is nothing but this is the flexibility coefficient F33, because that's what the way flexibility coefficient is defined, that F33 is the displacement along the degree of freedom 3 when we apply a unit force along the degree of freedom or the line of action of force 3 such that there is no other force acting. So this rotation is F33. Similarly, by this definition, the rotation in the anti-clockwise direction at the other end of the member, that is F66. So this rotation at the other end, this is F66. So here we assume that anti-clockwise directions are positive. Of course, here the member is bending such that at the other end the actual rotation is the other way, but that is not the positive direction. So here now we can see that no other force is generated except the reactions. So the structure is very determinate in nature and we can easily apply the principle of virtual work. So let's see how. Now we apply the principle of virtual work. So what we do, first of all, we treat this as our primary force system, and for this particular system we obtain the bending moment diagram. This we call as uppercase MX. Then we have to choose the point where we want the particular displacement. So coincidentally it's the same point. So at that point where we want the displacement, we apply a virtual force or the moment, because here we want rotation. So we have applied a virtual moment equal to 1. So the bending moment diagram for this particular case, that is the virtual force system, will also be exactly same, and we are designating it by M1x. Of course here the two are coincidentally same. Then when we equate the internal and the external virtual work, then we find that the external virtual work is F33 and the internal virtual work by definition would be again the product of uppercase m and lowercase m divided by ei integrated along the length of the member, so which boils down to the integration of m1x square divided by ei. So we can take care of ei in this manner and we can obtain the value of F33. Then next is that we have to find F63. So for that purpose we have to create another virtual system. So in this particular virtual system, we apply a unit moment along the other end, and for this also we draw the bending moment diagram, which is this. And by definition, when we do the equation of the external and the internal virtual work, we get this relation. So because here the work done by the virtual force is 1.f63, and this is the expression for the internal virtual work, and here the product of m1 and m2 will come into picture. So this is by definition f63. Next, by same logic, we can obtain other terms also. For example, if we want to obtain what is the value of f66, then all we have to do is that we apply the real as plus the virtual moments at this end of the member, and by the same logic as we have done for f33, we can find the value of f66 also. By analogy also, we can write directly this expression. So both ways you will be able to derive what is f66, and similarly f36 also you will derive, and you will find that by Maxwell-Betty's theorem it's same as f63 because the flexibility matrix is also symmetric in nature, and we get this expression. So once we have done this, then a lot of our problem is solved, but this is not exactly we want. What we want is this kind of system such that we are applying some displacement, here rotation, along a particular degree of freedom, which is the degree of freedom 3, and we want to find out how much is the moment required along that degree of freedom, and what are the forces generated along other degrees of freedom also. So what we do for this purpose, we use the principle of superposition. So all we have to do is that now we have solution A with us, that is we had applied the moment at the left end and we had solved this system, and at the same time we had applied the moment at the right end of the structure and we had solved this system also. So we have the systems A and B. So the point is that can we superimpose these two systems A and B and achieve a condition such that we have displacement only along one particular degree of freedom, that is the rotation, and all other displacements they are locked? Yes, this is possible. So if we apply the linear combination of A and B such that we are able to lock all rotation at the right end of the structure by their linear superposition, then we'll achieve this kind of system. So for this purpose, what we do, we combine these two cases, we do superposition in this particular proportion. So what we do, we have purposely divided case B by f66 and we multiply it by f63 so that we have exactly the same rotation, and then we subtract this modified B from A. In that particular case, we will have perfect locking condition at this end. So we get a situation something like this, that at the left end we have some moment and we have some rotation also. So by linear combination we find that the moment at the left end is unit moment and the rotation undergone is this value, and there is a carryover moment like this. So now we can apply the definition of the stiffness coefficient. What is stiffness coefficient? Stiffness coefficient is basically the force required to bring about a unit displacement along a particular degree of freedom. So here we are talking about Kii K33. So we are applying here a unit force and we are witnessing some rotation also. So the ratio of these two will give us the coefficient K33. So simplifying, we get this value. So this is how we have obtained K33. Similarly, by analogy or by direct solution, we can determine K66. So at least we have determined K33, K66 and K63 and K36. So at least 4 coefficients we have determined. Now I had asked a question to the class of last year, how do we proceed now? How do we obtain other values? So they gave an answer that we just use the flexibility coefficients, we form the flexibility matrix and we obtain its inverse. Inverse of the flexibility matrix will give us the 6x6 stiffness matrix. So that is one way. However, we'll use the other way, that first of all we have to determine the other remaining coefficients also. So what we do now, next target is that we have to derive K22. So what is K22? By definition, K22 is again the force required along the degree of freedom 2, such that we obtain a unit displacement along the degree of freedom 2 and all other degrees of freedom are locked. So this force will be by definition K22. So how do we derive K22 such that we can make use of what we have derived so far? So this is definitely an indeterminate structure and its solution is different. However, our solution becomes easier if we consider the following combination. That let us say we consider a pure cantilever structure. We have no restraint at the left end of the structure and we apply a unit force. We'll undergo some rotation here. Now this system is a determinate structure and we can very easily solve by the principle of virtual work and we can get the theta here. Now this, let's say, system A, we consider another system B, and in this system we apply a rotation equal and opposite to the first case. So this is the prop cantilever case, and if I ask you that how much moment is required to bring about this particular rotation such that this is opposite to the rotation in the case of structure A, then you will say that the answer is K33 theta, and K33 we have already derived. So that way what we have found that by superposition of A and B, the net angle of rotation at the left end is 0 and the beam has undergone the translation in this fashion. So it has undergone this kind of profile which we want. So when we see this, so what we have undergone is this kind of situation. So all we have to do is that we find out how much is the displacement undergone, and by this we can find out the force required to bring about per unit displacement, and this gives us the value of K22. So once we have obtained the value of K22, we can get other coefficients also. For example, at the other end, the carryover moment here, this will be K62 by definition, and the moment produced here, that will be equal to K36. So these can be obtained once we have K62, then the other one can be obtained by mere equilibrium. And in the same way, we can find out K55, that is, we apply the force along the degree of freedom 5, keeping all other displacements locked. So in that case, we'll get K55, K35 and K65. So once we have all these coefficients, then the next is how to obtain K11 and K41. So what are these coefficients? They are corresponding to the axial deformation. So for that purpose, we consider this system. So here on the top of this, we apply the principle of virtual work. So we apply here a unit force also in the same direction. Then when we apply the principle of virtual work, what is external virtual work and what is internal virtual work? And then is it a determinate structure? The answer is yes, this is our determinate structure. So when we consider the equation external and the internal virtual work, then we find that the external virtual work is simply the unit force multiplied by the deformation delta, and the internal virtual work when we have axial force is given by this expression. So where Fv is the axial force internal generated by the virtual force, which is unit, multiplied by the strain because of the actual or the real force, and this is basically the elongation of an infinitesimal element. So this is being multiplied by the force, so this gives us the internal virtual work done at an infinitesimal level, and when we integrate across the entire length, we get the total internal virtual work. And the strain can be then expressed in terms of the stress and the Young's modulus. So Fp is the internal force because of the actual loads, and A is the cross-sectional area. So we integrate this, so A is variable, so when we integrate, we get here the displacement. So we are applying some force and we are getting the corresponding displacement. So based on this, we can get the value of K11. So after this, now the last problem is that fixed-ended forces. We need fixed-ended forces also, because if we have member forces, then we have to convert them into equivalent joint forces. So this is the next problem we have to solve, that if we have, for example, a prismatic member and a member load is acting, it could be in any form, then how do we obtain the fixed-ended moments? So this will obtain by using the principle of superposition. So what we do, we just release the restraints and first we convert the structure into a determinate structure like this. So we just consider a pin roller conditions, and on this structure we can apply the principle of virtue work and we can find out what are the rotations at the two ends. Once we have done it, then we can use what we have derived so far. So what we do, we just superimpose three cases A, B and C. So A is this structure, the determinate structure we have just solved by the principle of virtue work, and we have the values of theta 1 and theta 2, the two end rotations. Now we superimpose structure B. So in that case, what we do, we apply rotation at the left end equal and opposite to the rotation here, so that we just try to counterbalance this rotation. So for that purpose, we have to apply here a force equal to K33 into theta 1, and K33 value we already have with us. So the carryover will be K63 into theta 1. And then C structure is that we nullify this rotation. So for that purpose, we apply a rotation equal and opposite to this theta 2 at the other end. So here the moment required will be K66 into theta 2, and there will be a carryover K36 into theta 2. Now we just superimpose A, B and C, and all we get is, when we superimpose, we get our original system, that is the structure with fixed-ended conditions like this. So the resultant moments at the two ends will be like this. We have just superimposed the various cases A, B and C. So here we are showing the results of the B and C, and the results of the A, we don't have any moment. So these will give us the values of the fixed-ended forces. So once we have done this, we can now solve any case of the non-prismatic member. So I give you a problem that we have this member, its length is L, and from the left end to the right end, the moment of inertia is becoming double and the area is also becoming double. So derive the stiffness matrix. So as a first step, what you can do, you just consider this structure to be prismatic section and try to derive K33 for prismatic section. Then you take it as per the actual and derive K33. And once you have K33 derived for the non-prismatic section, then you derive other coefficients also. So if you solve this completely, you will have a complete understanding of how the computations work. So thank you very much.